Generative adversarial networks, or the GANs. So these are a type of machine learning algorithm that can generate synthetic data that is nearly indistinguishable from this real world data. They work by pitting two neural networks against each other in a game-like competition, with each network trying to improve its performance by outwitting the other. The first network, known as generator, it creates synthetic data that it believes is real. The second network, called a discriminator, evaluates the data and tries to determine whether it is real or generated. As the generator improves its ability to generate data that looks and behaves like real data, the discriminator improves its ability to distinguish real data from generated data. And over time, both networks become more and more sophisticated and accurate, and ultimately reaches a point where it becomes difficult for humans to tell the difference between real and generated data. So these GANs have a wide range of applications, including generating images, text, and speech, as well as in fields such as computer vision, natural language processing, and machine translation. They have also been used to generate synthetic data for training machine learning models, reducing the need for large amount of real data. So how do these GANs work? So the working of these GANs can be thought of as a game between two neural networks, a generator and a discriminator. Now this generator will create a synthetic data that it believes is real, while the discriminator evaluates the data and tries to determine whether it's real or generated. So this generator network starts by randomly generating data that may not look like the real data. And this discriminator network then evaluates this data and gives feedback to the generator, indicating whether it thinks the generated data is real or fake. The generator then uses this feedback to improve its ability to generate data that looks more and more real and like this real data. At the same time, the discriminator network is also improving its ability to distinguish the real data from this generated data. It evaluates the real data and generated data from the generator and learns to become more accurate in its evaluation. And this process continues iteratively, with the generator and discriminator network improving their performance in parallel. And over time, this generated network becomes so good that it becomes difficult for the discriminator network to distinguish it from real data. And the generator network is able to produce realistic images that is nearly indistinguishable from real data. So in summary, we can say the GAN use a game-like competition between a generator and a discriminator network to create synthetic data that is nearly indistinguishable from this real world data by iteratively improving the performance of both networks. So how to calculate this GAN by hand? So GAN needs no introduction. It was invented by Ian Goodfellow in 2014. They're responsible for starting the field of generative AI for visual data. So let's go through the process. The goal is to generate realistic 4D data from 2D noise. So we are given 4 noise vectors in 2-dimensional, 4 real data vectors in 4 dimension. Generator first layer. So you will multiply the noise vectors with the weights and biases to obtain new features. Then generator ReLU, you will apply the ReLU activation function, which has the effect of suppressing negative values. So in this exercise, -1 and -2 are crossed out to 0 and they are set to the 0 values here, right? Then comes the generator's second layer. So here multiply the features with the weights and biases to obtain new feature vectors. ReLU is applied. But since every value is positive, there is no effect. So these new feature vectors are the fake data generated by this simple 2D generator network. Then we have a discriminator. So the first layer will feed both fake data and this real data to this first layer. So we will multiply both fake data and this real data with weights and biases to obtain new feature vectors. ReLU will be applied. Since every value is positive, there will be no effect. Then discriminator second layer. So here also you will multiply the features with one sets of weights and biases to obtain new features. And the intended effect is to reduce to just one feature value per data value. Then comes the discriminator sigmoid here, right? In this sigmoid function, you will convert the features to probability values using this sigmoid function. The sigmoid function is y is equals to 1 divided by 1 plus e raised to power minus z, right? So here we will apply this. So we will convert this feature z to probability values y using a sigmoid function. 1 means the discriminator is 100% confident that the data is real, and 0 means the discriminator is 100% confident the data is fake. Then we'll have a training. So we will compute the loss gradients of discriminator by the simple question of y minus yd. Why so simple? Because when we apply this sigmoid and binary entropy loss together, the math magically simplifies to this equation. So YD are the target predictions from the discriminator perspective. The discriminator must learn to predict 0 for the 4 fake data and 1 for the 4 real data. So here the discriminator loss involves both fake data and real data. So next we'll compute the loss gradients of generator by y minus yg. So yg are the target predictions from generator's perspective. So the generator must fool the discriminator into predicting 1 for the fake real data. So note that the generator's loss involves only the fake data. So with the loss gradient computed, we can kick off the backpropagation values. So you have got the overall idea. So let's start how we'll do it. So here we are given a noise sample and here it's given an input. So use our popular formula, that is y is equals to wx plus v. Now w means your weights, x means input matrix, right? Plus b is your bias, right? So these are popularly used for all the networks. So here we will check the number of columns as 3 and here the number of rows are 2. So consider the last one is bias here, right? So we will multiply 1 1 with 1 1. Getting 2 plus 0, right? Then 1 1 with 1 0, adding 0 here, right? So next we 0 1 with 1 1, adding this one. So we'll get this matrix here. Now we will multiply these two matrices so that we get this. So here check the number of columns as 4 here. Here number of rows are 3. So consider this one as the bias here, right? So here we will take minus 1 1 0, multiply this with 2 3 0. Here it's element wise multiplication and adding the bias here. So we'll get 1 here. Then minus 1 1 0 with 1 2 0 here. Because in the ReLU the negative values are considered as 0, right? So we'll take it like this 1 2 0. So do the multiplications, adding this bias terms here, will get this thing, right? Now we will go for multiplication of these two matrices, which will result in this, and then multiplying these two matrices will result in this. So here check the number of columns 1 2 3 4 5. Here it is 4. Consider the last one as the bias here using this formula w x plus b. So 1 0 0 minus 1, multiply this with a 1 2 3 1, adding 0 bias here will get 0. Then 1 0 0 minus 1, multiplying this with 1 1 2 1, adding 0 bias here will get this, right? So here we will continue for all the elements. Then we'll start with the second matrix here. Check here the number of rows are here the number of columns are 5, here the number of rows are 4. So consider the same formula, last one is the bias here. So 1 0 0 minus 1, multiply this with a 2 1 2 1, adding 0 bias here will get 1. Next 1 0 0 minus 1, multiply this with 3 1 3 1, adding 0 bias here will get 2. So similarly we'll do this. Next we will have the second layer here. Now check here the number of columns are 4, the number of rows are 3. Consider the last one as the bias. So 1 1 minus 1, multiply this with 0 5 3, adding minus 1, we'll get 1 here. Then 1 1 minus 1, multiply this with 0 3 2, So when we say this multiply, we means element wise multiplication. That is 1 is multiplied with 0 plus 1 into 3 plus minus 1 into 2 plus minus 1. We get 0 here, right? So here also we will do the element wise multiplications with both these matrices, which will result into this, right? Here also we'll consider the last term as a bias here. 1 1 minus 1 with 1 3 2, so 1 into 1 plus 1 into 3 plus minus 1 into 2 plus adding minus 1 here, we get 1 here, right? So we'll do for the other elements too, we'll get the things like this. Now we will apply the sigmoid function. Now this sigmoid function is equals to, that is equals to 1 divided by 1 plus e raised to power minus z. So we have got the z values, right? Okay. So we will take this formula. So here when we will apply for the first one here, right? Here it is 1 plus 1 divided by 1 plus e raised to power minus 1. So we'll get 0.7 here. Then we'll apply 1 divided by 1 plus e raised to power minus 0. So we'll get this one. So here we will use this formula and we'll get the results like this. Then we'll apply the same for this one. So here 1 divided by 1 plus e raised to power 1 minus 1. So that will result into this. So this we will get. Now we have this target values. So discriminator says it's all zeros. So here it's all 1, right? So the output should be y minus yd, right? Y minus yd. So just simply subtract both the things. Here also just subtract the things, right? So 7.7 minus 1 minus 0.3. You have got the things, right? So here it is for the discriminator. Now for the generator also y minus yg. So just subtract this thing, 0.7 minus 1. So we'll get minus 0.3. So subtract this from this, right? So we'll get the results like this. Hope it's clear. So to conclude this, we understood that we have done matrix element wise multiplication. So first multiplied both these matrices, we got this. Then multiplied this matrices, we got this. Then multiplied this with this, we got this. Multiplied this with this, we got this. Then multiplied this. Then multiplied both this. Then here we have taken this formula 1 plus e raised to power minus z. We got the values like this. Then we have done y minus yd, y minus yg. Here also we have subtracted it from this target values and we have got the results like this. Next comes the applications of this GAN. So these generative adversarial networks have a wide range of applications across various fields. Here are some examples. First is the image and video generation. So these GANs are commonly used for generating synthetic images and videos, such as creating realistic faces or landscapes. They can also be used for data augmentation, which involves creating additional training data by generating variations of existing images. Then comes image to image translation. So here GANs can be used to translate one type of image into another, such as converting black and white image into color image, or transforming the image of a room into a different style. Then comes text to image generation. So here the GANs can generate images based on textual descriptions, allowing for the creation of images that match specific prompts or requests. Then super resolution. So GANs can be used to increase the resolution of low resolution images, making them appear sharper and more detailed. Then comes inpainting. So here GANs can generate realistic images by filling in missing parts of image, such as repairing damaged or censored images. Then comes style transfer. So the GANs can transfer the style of one image onto another, allowing for the creation of images with unique styles and compositions. Then comes speech synthesis. So GANs can be used to generate synthetic speech that sounds natural and realistic. Then comes data augmentation. So GANs can be used to generate synthetic data for training machine learning models in various fields such as computer vision, natural language processing, and robotics. So these are just a few examples of the wide range of applications of GANs. As GANs continue to evolve and improve, so they are likely to have an increasing significant impact across many industries. Okay, thank you.